Alright friends, let's get started in 6.4. So we're continuing our discussion of functions. Excuse me. And in 6.3 we talked about composition of functions, which is an important topic. It's a way to make more complicated functions out of simpler ones. Another way that we can do that is doing some basic function arithmetic. So we can perform arithmetic operations like plus, minus, multiply, divide, right? On functions just as we can with numbers, okay? And the definitions are pretty straightforward, right? F plus g of x is just f of x plus g of x, right? F minus g of x is just f of x minus g of x. F times g of x is just f of x times g of x. And f divided by g of x is f of x divided by g of x. In each of these cases, the domain of the sort of resultant function, either the sum or the product or the quotient or whatever, the domain of that function is the domain of f intersected with the domain of g. That's for cases 1 through 3. In case 4, we have an additional restriction where g of x is not allowed to be 0. Okay, so the domain is the domain of f intersected with the domain of g, intersected with the set of all x such that the denominator is not 0. Okay, so let's practice doing some function arithmetic and stating the domains of the function, of the resultant function. So f of x is x minus 3, g of x is x squared minus 8x plus 15. So let's find f plus g and state its domain. Okay, so f plus g of x is going to be f of x plus g of x by definition. So this is x minus 3, right, that's f of x, plus x squared minus 8x plus 15, that's g of x. Generally, I think this is a little bit easier to grasp than composition of functions in the previous section. Anyway, we just combine like terms now. We're going to get x squared minus 7x plus 12. Okay, so there's f plus g. Now, if we're looking for the domain of f plus g, remember that the domain of f plus g is going to be domain of f intersect with domain of g. Now, what is the domain of f? F of x is this linear function. It has domain all reals, right? And g of x is a polynomial function. It also has domain all reals. So the domain of f plus g is going to be r intersect r, which is of course just r. So the domain of f plus g is all real numbers. Okay, so that's kind of boring. And that's going to be the same domain as parts B and C as well, because the domain of f plus g, f minus g, and f times g are always the same thing. So I'm not going to bother doing this second thing for parts B and C. But let's do part B. Right, f minus g of x, I need some more room. So I'm going to write it like this. This is going to be f of x minus g of x. So that's going to be x minus 3 minus x squared minus 8x plus 15. So x squared minus 8x. But then we distribute the negative sign, right? So we're going to have a negative x squared. We're going to have a negative 8, so that's a positive 8 plus 1 is plus 9x. And then we're going to have negative 3 minus 15, that's negative 18. Alright, so there's f minus g. And of course the domain of f minus g is all real numbers. Okay, let's do part C. F times g of x. Well, this is just going to be f of x times g of x by definition. So that's x minus 3 times x squared minus 8x plus 15. And we do all the distribution and stuff. We're going to get x cubed minus 8x squared plus 15x minus 3x squared plus 24x minus 45. And let's collect our like terms. We've got an x cubed. We have a negative 11x squared. We have a 39x, and then a negative 45, and that's it. Okay, the domain of f times g is the same as the domain of f plus g and f minus g. It's all reals. Okay. What about part D? So part D is f over g of x. So by definition, this is going to be f of x over g of x. So that's x minus 3 over x squared minus 8x plus 15. Now that's it, right? That's f over g. We might be able to simplify it, though. So let's see if we can simplify this. I think this is going to be x minus 3 and x minus 5, sure enough. So we can cancel the x minus 3's. We get 1 over x minus 5. Whoop, 1 over x minus 5. But now the tricky part is, if you're talking about the domain of f over g, it's not all real numbers anymore. Clearly, for example, x can't be 5, because if x is 5, you're going to get 1 over 0, which is undefined, right? So x can't be 5. But x also can't be x also can't be 3, because if you go one step previous, right, if you're just looking at f of x over g of x, right, when x is 3, you also get something undefined, right? You get 0 over 0, which is also undefined. So you can't just find f of x over g of x, simplify, and then find the domain of the simplified version of the function. You have to use the original g of x to find the domain of f over g, right? So remember, the domain of f over g is going to be the same as the domain of f plus g, f minus g, f times g, except that you have to kick out the values where g of x is 0. So as far as the domain is concerned, I need to make sure that g of x is not 0. That means x squared minus 8x plus 15 can't be 0. That means x minus 3 times x minus 5 can't be 0. And that means x can't be 3 and x can't be 5. So really the domain of f over g is going to be all reals except for 3 and 5. Right, so there's f over g, and here's the domain of f over g. Okay? So that, in a nutshell, is how function arithmetic works. Now, in this particular example, f and g were both polynomial functions, so they were relatively well behaved, right? There wasn't much to consider by way of domain considerations and things like that. So let me show you another one where it's maybe a little bit trickier with the whole domain issue. So here we've got f of x is square root x minus 1, and g of x is square root 3 minus x. So let's find f plus g and f divided by g. So we'll just do f plus g and f divided by g, and then part C is asking for something kind of a little bit different. But let's find f plus g first. So f plus g of x is going to be f of x plus g of x. That's going to be square root x minus 1 plus square root 3 minus x. And then if you can simplify that, you should. But in this case, I don't think there's any simplification that can really take place here. I think that's it, right? It's just going to be square root x minus 1 times square root of x, or 3 minus x. But now if we want to find the domain of f plus g of x, right? The domain of f plus g is going to be the domain of f intersect domain g. Well, so let's do some scratch work and figure out, well, what's the domain of f, right? Domain of f. So for f of x, we need for x minus 1 to be greater than or equal to 0. Which means we need x to be greater than or equal to 1. Which means the domain of f is 1 to infinity, right? The domain of g, for domain of G, we need 3 minus x to be greater than or equal to 0. That means we need x to be less than or equal to 3, right? If I move the x over here, I get 3 greater than or equal to x, which is the same thing as saying 3 greater than or equal to x, right? X less than or equal to 3. So we need so the domain of G is going to be negative infinity to 3. So back here to domain of f plus g, this is going to be domain f intersect domain g. That's going to be 1 to infinity intersect negative infinity to 3. And remember, the intersection is where these two sets overlap. And so I think they interlap from 1 to 3. We could draw a little picture. Here's domain of f. Here's domain of g. And so sure enough, the intersection is going to be from 1 to 3. So there's the domain of f plus g. So so this is really interesting, right? So this function, this sum, is not defined for most numbers. It's only defined between 1 and 3, right? Which is kind of an interesting thing. Okay, so there's part A. Part B asks us for f over g of x. And f over g of x is going to have the same domain as f plus g, except that we also need to require that g of x not be 0. So let's do this. This is f of x over g of x. That's square root x minus 1 divided by square root 3 minus x. And technically, you know, this is not considered simplified because you have a radical in the denominator. So we would multiply by the square root of 3 minus x in this case to rationalize. And if we do that, in the numerator, since the radicands don't match, the square roots are not going to cancel. What you really have is, you know, square root a times square root b kind of situation, which we know from the past is just square root of a times b. So I need to multiply the radicands. They're both binomials, and so that means I have to FOIL. I'm going to FOIL a little different because I want to write this in descending order. So I'm going to do x times x is, well, x times negative x is negative x squared. So I'm going to have square root of negative x squared. Then I'm going to get a positive 3x and a positive x. So that's going to make a positive 4x. And then I'm going to have a negative 1 times 3 is negative 3. Okay, so there's the numerator. In the denominator, on the other hand, since the radicands match, this is just square root of 3 minus x squared. So the radicals will just cancel and leave us with 3 minus x. So now, this is kind of strange because this, to me, doesn't look more simple than that. This looks worse than that, in my opinion. But this is considered simplified, and this isn't because you don't have any radicals in your denominator, right? So we're going to say there's f over g right there. Right? So there's f over g. Now, the domain of f over g is domain of f intersect domain of g intersect the set of all x such that g of x is not 0. So let's figure out what that set is. I mean, we know that domain of f is 1 to infinity. We already did that work. And we know that domain of g is negative infinity to 3. So we already did that work. But we need to figure out what this set is. Set of all x where g of x is not 0. So we need for g of x. So I'm going to do a little bit of scratch work. Okay, so we need g of x to not be 0. That means we need square root of 3 minus x to not be 0. That means we need 3 minus x to not be 0, right? Square both sides. That means we need x to not equal 3. So this set here would be, you know, all of the real numbers except for 3. Right? So we could say, well, it's all reals except for 3. So what does this all mean, right? So we know that 1 to infinity intersected with negative infinity to 3 is just 1 to 3. But now we have this additional restriction where x is not allowed to be 3 itself. So instead of having a square bracket on the 3, I'm just going to have a rounded parenthesis since x is not allowed to be 3. Right? So the domain of f over g in this case is going to be 1 to 3 with a parenthesis on the 3. So a subtle difference in the domain between between parts A and parts B, but there is a difference, right? In part A, x is allowed to be 3. In part B, x is not allowed to be 3. Otherwise, their domains are the same. Okay, and then part C. Like I said, part C is asking us for something really quite a bit different than parts A and B. It's asking us for a specific function value. So it's not asking for f of g of x. It's just asking for f of g of 2. There are two ways that you could go about this. One thing that you could do is you could find f of g of x and then plug in 2. Or you could just use the fact that f times g of 2 is going to be f of 2 times g of 2. Either way, you'll get the same answer. I think the second way is probably a little bit quicker, so that's what I'll do. So I'm going to say f times g of 2 is going to be f of 2 times g of 2. F of 2 is the square root of 2 minus 1. G of 2 is the square root of 3 minus 2. How boring. So this is the square root of 1 times the square root of 1. That's just 1, right? So there's f times g of 2. If we wanted f times g of x, right? So that's one way that you could do it. Another way you could do it would be to find f times g of x, which would be f of x times g of x. That would be square root of x minus 1 times square root of 3 minus x. And fortunately for us, we've already done this multiplication in part B. Right? It was negative x squared plus 4x minus 3. And so that's f times g of x. So if you wanted f times g of 2, well then you would just plug this in, right? It would be square root of negative 2 squared plus 4 times 2 minus 3. That's going to be negative 4 plus 8 is positive 4. 4 minus 3 is 1. Square root of 1 is 1, right? Sure enough, you get the same answer. But as you can see, I think this way is a little bit quicker if you're just asked for a specific function value. Okay, so that's that. So function arithmetic, pretty straightforward. Now, as we saw in the previous section in 6.3, it's often useful in calculus to think of a complicated function in terms of simpler ones. And we saw how to, we practiced doing this when it came to composition of functions, right, in 6.3. But we can do this with function arithmetic as well, you know, addition, subtraction, multiplication, division. So if you have this really big, nasty function here, this is really overwhelming to look at right at first. But if you can break it down into its smaller chunks, what you can recognize is that this is really some function divided by some other function plus, you know, the square root of some other function, right? So in other words, we can rewrite f of x as, you know, p of x over q of x plus g of h of x, where p of x is, you know, x squared minus 5x, q of x is x plus 1, g of x is the square root function, and h of x is x squared minus 3. So that when you compose g of h of x, you're going to get square root of x squared minus 3, right? Square root of x squared minus 3. So this chunk of it, right, the g of h of x bit, we practiced that in 6.3. So really the only new thing is that we can also describe things as not just as compositions, but as divisions or additions, right? Multiplications, subtractions. So let's practice doing that because that's going to be hugely important in calculus, and I'll show you on the next page where that comes in handy a lot of times. But okay, so let's say that g of x is x squared, h of x is square root x, p of x is sine x, and q of x is absolute value of x. Let's see if we can rewrite each of these functions as sums, difference, products, quotients, and compositions of g, h, p, and q and maybe we'll have some constants going on as well. But let's see, part A, we have f of x equals square root x plus absolute value x. Well, that one's pretty straightforward, right? Square root of x we called that h of x, so this is just h of x. And absolute value of x, we called that q of x, so this is just h of x plus q of x, right? And that's all there is to it. Part B. Go ahead and give the video a pause, see if you can do part B. Okay, here's my solution. I'm going to say, obviously x squared is g of x, so I'm thinking this is g of x times sine of x, we called that p of x. So this is g of x times p of x minus 2 times the square root of x, we called that h of x, right? So it's g of x times p of x minus 2 times h of x. It should go without saying there's more than one way to do this, right? Like the 2 times square root of x, you could have been clever maybe and said, you know, this is x squared sine x minus root x plus root x, right? Since root x plus root x is 2 times root x. And so then you could have said, you know, this is minus h of x plus h of x or something. So instead of saying 2 times h of x. But this does the trick. Part C, do this in 2 ways. Yeah, pause the video, see if you can do part C in 2 different ways. Okay, here's my solution. One of the ways that occurs to me to do this is to think of sine squared as just sine x times sine x. So, of course, that would just be p of x, right? We called sine x p of x. So this would just be p of x times p of x. So that's one way to do it. Another way to do it, though. Well, sine squared x is just sine x squared, right? This is just a different notation for saying this. So what we have is p of x squared. Now what's the square function? We called that thing g of x. So this is going to be g of p of x, right? We're plugging p of x sine x. We're plugging p of x into g, which is the square function. So you could also think of it as g of p of x. Notice how important it is to keep these notations straight. This is not g times p, it's g of p. You're plugging p of x into g. Whereas this is p times p. You're not plugging anything into anything else. You're just multiplying p of x times itself, right? Sine x times sine x. But in this case, you end up at the same place if you take g of p of x, or if you take p of x times p of x, right? You end up at sine squared x in either case. Okay, part F, we have absolute value sine of x squared. Be careful now. Sine of x squared is not the same thing as sine squared x, right? This is not sine x squared, it's sine of x squared. You're squaring the argument, not the function value. So pause the video, see if you can do this one. Here's my solution. I'm thinking of this as just a composition inside of a composition, right? Like the outermost function is the absolute value, which we called q. Okay? Then inside of that you have the sine function, which we called p. And then inside of that you have the square function, which we called g. So I'm going to call this q of p of g of x. Okay, things are starting to get a little more interesting in parts E and F. We have a little bit more going on. See if you can do part E and F, yeah. So see if you can do part E, give the video a pause. Okay, here's my solution. I see the square root function. Now the square root's not covering the -2, but that's okay. We can just write, you know, -2 at the end of whatever function stuff we have going on inside here. So I think we have the square root of some function. So the outermost function here is the square root function, which we called h. So this is going to be h of something. H of what? Well, h of sine of absolute value of x. So h of sine. Sine function was p. So this is h of p of absolute value of x. Absolute value of x we called q. So this is h of p of q of x. But now let's be careful, right? Because that just takes care of sine of absolute value of x. Then we have plus 1 still on the outside that we are still taking the square root of. Okay? So we've got the square root of sine of absolute value of x plus 1, right? So that takes care of the stuff inside of the square root. And then we're just subtracting 2 from that. So that's what that function looks like. Okay, last one. Give the video a pause, see if you can do part F. Okay, here's my solution. So I noticed here that I've got a product. I've got a 3x squared plus 1. I didn't have a function that was called 3x squared plus 1, but I did have a function called x squared. We called that thing g. So I think this is going to be 3 times g of x plus 1. That takes care of that first chunk, times the square root of x, which we called h of x, divided by x squared, which again we called g of x, then minus sine of square root of absolute value of x. Sine function was p, square root function was h, absolute value function was q. So that's that one, okay? Okay, so the better we can get at recognizing sort of the little functions that make up our bigger, nastier function, the easier it's going to be to do things like take limits, find derivatives, integrate, which are all things that you're going to do a lot of in calculus. So let me just show you, as far as derivatives are concerned. So this is just where this is useful for derivatives. Of course, it's, as I said, useful for other things as well, limits and integrals. But as far as derivatives are concerned, we saw the chain rule for derivatives in the previous section, right, 6.3. But we also have sum and difference rules, product rules, and quotient rules for whenever we're looking at functions that are sums of smaller functions or products or quotients. Okay, and we're not going to practice applying these rules, of course. That's something that you'll do in calculus. So I'm not gonna get into how these rules are applied. But what I did want to do is just show you these rules so that you understand why I want you to develop the habit of seeing a function as a sum, product, difference, quotient, or composition of smaller functions, because you're going to have to be able to do that in order to apply these rules for taking derivatives of really complicated functions. And while we're on this topic, let's practice some algebra involved here, okay? So for each of the following, a function is given along with its derivative after application of the chain rule, sum difference rule, product rule, or quotient rule. And I just want to practice simplifying the derivative, okay? So the parent function, the original function, is just given sort of for your information, right? It's not really necessary in order for you to simplify the derivative, which is this thing right here, right? So really, I just want to simplify this function. But I just wanted to show you what kinds of things you get when you apply. In this case, we would be applying the quotient rule, right? We would be thinking of this as some function divided by some other function. And when you apply the quotient rule, you get this big nasty thing. So let's practice simplifying it. So one way that this could simplify is if I had a factor of 3x minus 5 in both of these terms up here, right? Like I'm thinking of this whole thing as one term and this whole thing as a second term. I have a 3x minus 5 as a factor in this first term, but not the second one. So that means, at least the way that it's written right now, I'm not going to be able to cancel off a 3x minus 5 anywhere. But maybe if I distribute the 3 here, FOIL this out, and then combine like terms, I might be able to refactor the numerator, and maybe it has a 3x minus 5 in it. I don't know. Even if I can't, I should still at least simplify the numerator. So let's get busy doing that. We're going to get a 6x squared, a 9x minus a 10x. That's going to be minus x. And then minus 15. Here I'm going to have minus 3x squared. So I'm going to distribute the 3 and the negative sign as I go. So then I'm going to get 9x, but it's going to become negative. And then I'm going to have a negative 3, but it's going to become positive. Six x squared minus 3x squared is 3x squared. Negative x minus 9x is negative 10x. And negative 15 plus 3 is negative 12. Still not sure if we can, if we're gonna get a 3x minus 5 out of this stuff. I kind of think we're not going to. It doesn't seem like it anyway. Because 12, I mean, you get 12 by doing 3 times 4, or by doing 6 times 2 maybe, or 12 times 1, but none of those things are going to give you a 5. In fact, I wonder if you can even factor the numerator at all. There's so many possibilities for 12, it's kind of hard to think through them all. So let me think about this for a second. 6 times 2, you'd get an 18, or a 12. Maybe 6 times 2. Let's see. So I'm thinking, well, if I do 6 and 2, then I'm going to get 6 and 6. That's not going to work. But if I do 6, 6 and 2, that'll give me 18. Oh, no, 6 and 2 won't work. 3 and 4. I could do 4 here. That would give me 12. And I'd have to do 3 there. That would give me 9, best case scenario. So that's not going to work either. 12 and 1 would again give me 9. Yeah, I don't know. I don't think this thing factors. 6 and 2, 12 and 1, 3 and 4. Yeah, I don't think it's going to factor. So I think this is as simplified as this one gets. Okay? That's a little disappointing. I was hoping the numerator would factor and then we'd be able to cancel with something in the denominator, but that's okay. It doesn't always work out like that. Okay, part B. Same deal. You're just given the original function, ln of x squared plus 1 times square root of x squared plus 1. You're just given that just kind of for your information. What you really want to simplify is this derivative. Now you get this derivative by applying a product rule, and inside of the product rule you have some chain rules going on. Here this one is a whole bunch of chain rules. So you get this really nasty thing, right? Let's see if we can simplify it. So one thing that might be useful when I'm thinking about simplifying these things is anywhere I see a square root, I think I'm going to, well, that's only here, but I think I'm going to write that as an exponent instead of a square root. And then I'm also going to rewrite all of my terms as fractions. So in other words, I have 1 over x squared plus 1 times 2x over 1 times x squared plus 1 to the 1/2 power over 1. Right? That's that first term. And then the second term, I'm going to do the same thing, right? So I'm going to have a plus ln of x squared plus 1 over 1 times 1/2 times. Now this negative exponent, I'm going to flip this over and call this 1 over x squared plus 1 to the positive 1/2. And then I have a 2x over 1. The reason I set it up this way is because, first of all, you've got this sum. So you should like simplify each of these terms sort of individually, okay? But it's easier for me to see where things are going to cancel. Like right here, for example, you can cancel anything that are anything that's in the numerator. You can cancel with anything in the denominator. So for this first term in particular, this is an x squared plus 1 to the first power. So I can cancel off the x squared plus 1 to the 1/2 here and cancel it off there, and I'm going to be left with an x squared plus 1 to the 1/2 there in the denominator, right? And I think that's all of the canceling I get, but now I'm going to combine all of my numerator and denominator. 1 times 2x is 2x, right? And this was just 1 as well. Divided by x squared plus 1 to the 1/2 times 1 times 1. Well, so that's just x squared plus 1 to the 1/2 power. And already that first term is looking quite a bit better, quite a bit more simple. Let's do the same thing for the second term. I don't get much cancellation in the second term. The 2's cancel, so that's nice. But then be careful, right? This x squared plus 1 to the 1/2 is not going to cancel with this x squared plus 1, because you're not looking at ln times x squared plus 1. No. You're looking at ln of x squared plus 1. You're taking the ln of this value. You can't just cancel it. So what do we have altogether? We've got an x times ln of x squared plus 1 divided by x squared plus 1 to the 1/2 power. So the second term is looking a lot better now. And would you look at that? You've got the same denominator. And that means you can go ahead and add these two rational expressions together. By the way, if you didn't have the same denominator, you could get a common denominator, right? And then add the rational expressions. In this case, it works out nicely for us because we already have a common denominator. So this is just 2. Oh, and you know what? I can factor out an x. Yeah, let me do that. We're going to have x times 2 plus ln x squared plus 1 divided by x squared plus 1 to the 1/2 power. So there you go. If you didn't distribute, or if you didn't factor out the x and you just had, 2x plus ln, or plus x ln of x squared plus 1 over x squared plus 1 to the 1/2, that would be fine, right? This is still perfectly simplified. But I kind of like factoring if I can, if you can factor, then that's nice because that means that you can cancel stuff often. Okay. One last thing I want to do. So we've talked about creating complicated functions out of simple functions by doing composition of functions, right? We talked about that in 6.3. But then in this section, we also talked about adding, subtracting, multiplying, and dividing functions in order to create more complicated functions. Or a better way to think about it is we can think of really complicated functions in terms of these simple building blocks that they're made out of, right? But another way that we can create new functions out of old ones is to form piecewise functions, which we've already seen, right? We saw piecewise functions back in section 1.4 at the beginning of the course. But it's maybe been a while since we've looked at piecewise functions, so let's remind ourselves how these things go. The main trick to graphing these is to figure out what's happening close to where the rule changes. So, for example, if we have this piecewise function f of x equals x squared if x is less than or equal to -1, or 2x if x is greater than -1, and we wanted to graph this thing, then a good thing to do would be to figure out what's happening right at -1. Okay, so and we're going to do that when we look at f of -1, but we'll also do that by looking at some limits potentially. So let's do this, right? So first of all, part A asks us to find some function values, f of -2. For f of -2, -2 is definitely less than -1, so we're going to be using the top rule, right? So f of -2 is going to be -2 squared, which is +4. f of 3, well, 3 is greater than -1, so for 3 we're going to use the bottom rule. Right, so f of 3 is going to be 2 times 3, which is 6. f of -1, Well, -1, of course, equals -1. So we're going to use the top rule, right? So this is going to be -1 squared, which is +1. So we could plot those points, right? We know that f of -2 is 4. We know that f of 3 is 6. 2, 3, 4, 5, 6. And we know that f of -1 is 1. That doesn't give us a very good picture so far, but hey, it gives us a starting point. So a good thing to do would be to look at some limits here, right? If we look at the limit as x approaches -1 from the left, okay? If we're approaching from the left, that means we're going to be approaching from values that are slightly less than -1. So we're going to be using the top rule in all of these cases, right? So what value are we approaching? We're going to be approaching -1 squared, which is +1. What's the limit as we approach -1 from the right? Now, as we approach -1 from the right, we're going to be looking at values for x that are slightly bigger than -1. So we're going to be using the bottom rule for each of those values. So what value are they approaching? Well, they're going to be approaching 2 times -1, which is -2. So what that tells me is that even though f of -1 is 1, the limit as we approach from the right is going to be -2. So I've got a hole right here at -2, and then the function kind of jumps up to that one. Okay. And now I think I have a pretty good idea of what's going to be going on here. Okay. So on the left-hand side, right, when x is less than -1, so on the left-hand side of this graph, I'm graphing this parabola. It's a parabola centered at, or with vertex 0, 0, except that x is less than or equal to I'm only using this rule if x is less than or equal to -1. So I'm not going to plot this portion of the curve. I'm just going to start here and plot this parabola. Okay. So this is -1, 1, -2, 4. I'm also going to have -3, 9, 4, 5, 6, 7, 8, 9. All right. On the right-hand side of the function, I'm going to have this straight line, right, 2x. So that's an intercept of 0 and a slope of 2, right? Up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. Sure enough, right? So we've got this straight line from -1 to infinity. Okay, so that's what that function looks like. Okay, so you're on this parabola until you hit -1, and then right after -1, you jump down to this straight line. Okay. All right. Another approach to graphing these things. Let me pull out a pencil. So another approach to graphing these piecewise functions is to just plot the entire function and then erase the parts that don't correspond to what you're trying to graph. So for example, if I wanted to graph x squared, like I said, it has a vertex at 0, 0, and then it goes through 1, 1, 2, 4, right, and so forth. So if I were to graph the entire parabola, right, it would look like this. And if I were to graph the entire line, it would look like this. And so if I wanted to graph the piecewise function, I would just erase the parts that don't correspond to the domain that I'm working with, right? Because I'm only going to use f of x equals 2x if x is greater than -1. So I would go back and erase all of the stuff less than -1. And I'm only going to use x squared if x is less than or equal to -1. So I'm going to erase all this stuff to the right, leaving me with that piecewise function that I started with. So you could also do that, right? Just use a pencil and erase, graph the whole function and then just erase the parts that don't correspond to the given domain. Okay, so let's look at another one. Here we've got a slightly more complicated situation. but actually not that complicated, I suppose. We've got absolute value x plus 1 minus 4 if x is less than 0. 2 to the x plus 1 if x is greater than 0. What happens if x equals 0? Well, if x equals 0, we're just going to use negative 1. Okay? So first of all, let's figure out these function values that we're asked for. F of negative 2. Negative 2 is less than 0, so we're going to use the top rule, right? This is going to be absolute value of negative 2 plus 1 minus 4, which is going to be negative 3 at the end of the day, I think. For f of 3, 3 is definitely greater than 0. So we're going to be using the middle rule. This is going to be 2 to the 3 plus 1. That's 2 to the 7th, or 7, 2 to the 4th power, which is 16. And then finally we're asked for f of 0. When x equals 0, we're going to be using the bottom rule. F of 0 is just negative 1, right? It's just negative 1. So we can plot those 3 points. We've got negative 2, negative 3. We've got 3, 16. Oh, that's going to be off the page. 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 11, 12, 13, 14, 15, 16. I mean, it's somewhere up here, right? Anyway, and then f of 0 is negative 1 right there. Maybe that doesn't give us a huge amount of help, but notice that the place where the rule changes is right at 0. So I'm interested in looking at some limits, right? Limit as x approaches 0 from the left of f of x. If I'm approaching from the left, I'm going to be plugging in values slightly less than 0, which means I'm going to be using the top rule. So what value am I approaching? I would be approaching absolute value 0 plus 1 minus 4. Uh, 0 plus 1 is 1, absolute value of 1 is 1, 1 minus 4 is negative 3. So as I approach from the left, f of x is approaching, as I approach 0 from the left, f of x is approaching negative 3. So I have this hole right there. What about as I approach from the right? So as I approach 0 from the right, I'm going to be plugging in values slightly larger than 0. That means I'm going to be using the middle rule up here. So what value am I approaching? I would be approaching 2 to the 0 plus 1, which is 2. So as I approach from the right, I'm approaching 2. Okay? Now maybe I still don't have a great idea of what this thing looks like, but well, I think we can figure it out, right? So if x is less than 0, so if I'm on this half of the graph, I'm going to be graphing absolute value of x plus 1 minus 4. This is an absolute value function with vertex negative 1, negative 4. So negative 1, 2, 3, 4. There's the vertex. And yeah, so it's going to go up to this value, but never quite reach it, because right when we get to x equals 0, we change rules to this thing, right? So, so that's what the left-hand side of the graph looks like. You know, a little backwards check mark. What does the right-hand side of the graph look like? Well, the right-hand side of the graph is going to be 2 to the x plus 1. This is an exponential function that's been shifted left 1 unit. So, you know, 2 to the x would go through 0, 1, 1, 2, negative 1, 1/2. But this thing has been shifted left 1 unit. So 2 to the x plus 1 is going to go through negative 1, 1, 0, 2, and negative 2, 1/2. So 0, 2, sure enough, right? 0, 2. Except that it doesn't actually go through that. F of x doesn't go through that point because we're only going to use 2 to the x plus 1 if x is greater than 0. But definitely So negative 1, 1's not going to be on there either. 0, 2 we've already plotted as an open circle. Negative 2, 1/2 is also not going to be on there, but I can kind of tell what's going on, right? Like if I plug in 1, I'm going to get 2 to the 1 plus 1. That's 2 squared, which is 4. 1, 2, 3, 4. And I'm expecting some exponential growth. If I plug in 2, I'm going to get 2 cubed, which is 8. 4, 5, 6, 7, 8. And then 16, right? So it's starting to grow exponentially like this on the right-hand side of the graph. And that's what that looks like, right? So a little backwards check mark and then an exponential that's growing really fast here. It doesn't do the normal exponential thing where it gets closer and closer to the x-axis the other way because we're not using this rule when x is less than 0. When x equals 0 itself, f of x is just going to be negative 1. So that's what that function looks like. Okay, so that's all I have to say in this section. In the next section, I think we're going to be talking more about these kinds of translations of functions. So stay tuned. We'll see you in the next one.